The Hardy-Weinberg Equilibrium Principle states that allele and genotype frequencies will remain constant in a population from one generation to the next, as long as there are not any other evolutionary influences. In order to ensure a population is not affected by evolutionary forces, certain conditions must exist. There cannot be any selection, migration, or mutation. The allele frequencies must be equal in both sexes. The generations cannot be overlapping. The populations must be large, and the mating must be random. This is obviously non-realistic, but nevertheless, the Hardy-Weinberg principle does provide valuable information about hereditary trends. There are two formulas that are part of the Hardy-Weinberg principle, and they are listed here in this box. I will go through what the variables mean as well as what the terms indicate. Let's assume that a gene has two alleles, capital A and lowercase a. P would be the frequency of the dominant allele, capital A, and Q is the frequency of the recessive allele, lowercase a. Since frequency is a percentage of 100 in a decimal form, it makes sense that when you add P and Q together, you would get 1, which is 100% of the population because there are only two possible alleles in this population, A and A. P squared, therefore, would be the frequency of the homozygous dominant genotype, capital A, and Q squared would be the frequency of the homozygous recessive genotype, lowercase a. And 2PQ would be the frequency of the heterozygous genotype, capital A, lowercase a. You'll notice that the second equation is a variation of the quadratic. It does have the terms in order to be factored. And if I was to factor the second equation, I would get P plus Q times P plus Q, the first equation. So there are definitely some underlying math principles at work here. Today I'll go through the steps for how to solve Hardy-Weinberg equilibrium problems, and I think the best way to do this is just to jump right in and do a problem together. So let's talk about squirrels. Imagine we have a population of squirrels that can be either gray or brown. The gray allele has complete dominance over the brown allele. So the gray allele is indicated with the capital G and the brown allele is indicated with a lowercase g. We are told the total population of squirrels is 2,874, and we are told that 2,292 of them are gray, which is the dominant phenotype. We need to determine several things. We need to determine the allele frequency, the frequency of individuals for each genotype, as well as the number of individuals for each genotype. Let's take a look at the steps up above. The first step, to calculate the frequency of homozygous recessive genotype, which is Q squared, we need to take the number of recessive individuals and divide it by the total number of individuals in the population. Well, I already know what the total number of individuals in the population is. That's 2,874. And if 2,292 are gray, which is the dominant phenotype, that means that if I subtracted the dominant from the total number, I should get the number of individuals who exhibit the recessive phenotype. That's 582 would be my homozygous recessive. So if I take 582 and divide it by 2,874, I would get 0.2025. I'm using 4 significant figures for this problem, which would be our Q squared value. I suggest that when you do get one of your values that are listed up in the table above, you go ahead and box it so that it's easy to find later. And you know what? I'm going to go ahead and box this as well. We have just completed step 1, finding the Q squared value, which is the frequency of the homozygous recessive genotype. Step 2, we need to find the frequency of the recessive allele by taking the square root of Q squared. Easy enough. So go ahead and take the square root of 0.2025. You will get 0.45, which is equal to Q. Step 2 is done. Step 3. We're going to find the frequency of the dominant allele P using that first Hardy-Weinberg equation. The first equation states that P plus Q is 1, so modifying that to solve for P, we would see that 1 minus Q should give us P. So coming back here to our problem, if I know what Q is, 1 minus that Q value would give me P. So 1 minus 0.45 is 0.55, which is my P value. Now I have my P and my Q value, I can basically do anything with this equation, with this problem. All right, looking at step 4. We're going to calculate the frequency of the homozygous dominant genotype, P squared. So taking my P squared value, I'm going to go ahead, taking my P value, I'm going to go ahead and figure out what the P squared is. P squared is 0.3025. I'm just squaring that P value. I'm going to box this. We have completed step 4. Step 5, to calculate the number of individuals with the homozygous dominant genotype, I take that P squared value and I multiply it by the total number of individuals in the population. So that P squared value, I'm going to go ahead and multiply that by the total number. So we'll take this 0.3025 and multiply that by all of the squirrels, and I will see that I have 869 that are going to be homozygous dominant. We have just completed step 5. Step 6. Calculate the frequency of the heterozygous genotype. That's 2PQ. Okay, we can do that. We know our P, we know our Q, so let's go ahead and figure out what that is. 2PQ is just going to be 2 times 0.55 times 0.45. So 2PQ is going to be 0.495. I'm going to rewrite that as 2PQ. I like to have my answers boxed. We have completed that step. Now, for the following step, very similar to step 5, to calculate the frequency of the heterozygous genotype, we take that 2PQ value and multiply it by the total number of individuals in the population. So I'm going to take this 0.495 and multiply that by the total number of individuals in the population, and that's going to give me 1423 that are heterozygous. We now have all of our values. Let's look closely. Determine the allele frequency. That's my Q and my P value. I have those, 0.45 for Q and 0.55 for P. Determine the frequency of individuals per genotype. I have those. I figured out from the very beginning that there were 582 homozygous recessive, and if you want to check that, you can always do what we did with the other values. Take that Q squared and multiply it by the total number of individuals, and you'll see I do get 582. So this is correct. I also know that there are 869 homozygous dominant, and there are 1,423 heterozygous. Since those should all add up to the total number of squirrels, you can check your answer by doing 582 plus 869 plus 1423, and you would see that they do in fact add up to the total number of squirrels, which is really more of my individuals per genotype, so that was more of this one. Individuals per genotype, I skipped ahead there, would be this number, and this number, which should add up to the total number. So we're good there. Now, in terms of the frequency of individuals per genotype, that's going to be our P squared, 2PQ, and our Q squared. And using our second Hardy-Weinberg equation, those should add up to 1. So if I took this value plus this value plus this value, they do equal 1. So that's another way I would check my answer. Lots of places where you can check and make sure that your numbers are making sense. So coming back up here, we figured out the frequency of the homozygous recessive genotype, that's our Q squared. Then the frequency of the recessive allele, which was just Q, and the frequency of the dominant allele, which was P. Once we had Q and P, we were able to work through and figure out the frequency of all the genotypes as well as the number of individuals with each of those genotypes, following these steps here. And then we were allowed to check to make sure our numbers make sense by substituting them back into the second equation and by adding our values together for the number of individuals in the population to make sure it added up to the total number of individuals. Just to make sure this is making sense, let's do one more example together. The ability to taste PTC is due to a single dominant allele T. A scientist sampled 356 individuals and determined that 74 could not detect PTC. Just like before, we're going to determine the allele frequency, the frequency of individuals for each genotype, and the number of individuals for each genotype. Let's go through our steps. Our first step, we calculate the frequency of the homozygous recessive genotype by taking the number of recessive individuals and dividing it by the total number of individuals in the population. So here, I know that the number of people who could not detect PTC would be our recessive, that's 74, and the total number of people sampled is 356. When I take 74 divided by 356, I get 2.08. I'm using 3 sig figs here, which is my Q squared value. As you learned from before, boxing these is helpful. So we have just completed step 1. Step 2 is pretty easy. Find the frequency of the recessive allele by taking the square root of that number we just got. So let's go ahead and square root our 0.208, and that's going to give us 0.456, which is our Q value. In order to find our P value, we modify that first equation so that P is equal to 1 minus Q. I'm looking at step 3. So I'm going to do 1 minus that Q value to get my P value, and I'm going to box it. Now that I have my P and my Q, I can basically just go through all the rest very simply. We'll take a look at step 4. We'll calculate the frequency of the homozygous dominant genotype by squaring that P value. So I'm going to take this P value and square it. P squared is therefore going to be 0.296. That's my frequency of individuals that have the homozygous dominant genotype. And if I want to find the number of individuals that have the homozygous dominant genotype, step 5, I just multiply that by the total number of individuals in the population. So I'm going to take the 0.296 and multiply that by the 356 in the population, and I'm going to see that 105 would be homozygous dominant. We'll box that. Going fast through these, we're doing good. Look at step 6. We'll calculate the frequency of the heterozygous genotype, 2PQ. Since I know P and Q, this should be very easy to do. So 2PQ would be 2 times 0.544 times 0.456. That's going to give me 0.496, which is my 2PQ. And just like we did with the previous problem, to find the frequency of individuals with that heterozygous genotype, step 7, I take that 2PQ value and I multiply it by the number of individuals in the population. So I'm going to take that 0.496 and multiply it by the number of individuals who are sampled, and I'm going to get 177 that are heterozygous. Now we have all of our information. We can check our values. We can take our P squared, our 2PQ, and our Q squared and add them together and make sure that it equals 1 according to the second Hardy-Weinberg equation, and it does. So we're pretty good there. We can also take our frequencies for each the number of individuals for each genotype, and make sure it adds up to the total number of individuals. So I know that there are 105 homozygous dominant, 177 heterozygous, and 74 homozygous recessive, when I add those together, I do get the total number of 356, so we are good there too. It is important for you to check and make sure that your numbers are making sense, they are adding up. That way you can catch your mistakes along the way, so checking your frequencies and checking your total numbers is valuable. I'll include a link for this PDF as well as the 2 examples on the second page so that you can follow the steps and have the equations and have an example all in one place in your binder to refer to. I'll also include some links for other helpful biology resources as well as any other science, math, test prep, anything that you really need in our student handbook.